Hi guys, in my last lecture we discussed some basics of EDC, definitions, notations and small formulas. So today's lecture will be just a continuation of your previous one. So let's start with lesson number 2. Leakage current. In the bracket I have provided the notation of leakage current. Leakage current is also called minority carrier current, reverse saturation current or thermally generated current. Now why it's thermally generated current? Thermal is a name related to temperature, so something will be related to temperature. Your leakage current depends on minority carriers and minority carrier concentration depends on temperature. Leakage current is generated only because of temperature, so that's why it's known as thermally generated current. It's a saturated current. Now why it's saturated current? Your thermally generated current was independent of applied voltage and hence it remained constant, and when it's remained constant it is a saturated current. Third, for germanium it's microampere and for silicon it's nanoampere. So this thing I have indicated in this block, that for germanium it's greater than silicon. Leakage current for germanium is greater than leakage current for silicon. Leakage current should be less. That means minimum the leakage current, better is the material. So silicon is preferred than germanium. Silicon is having better thermal stability than germanium. This is what I have mentioned in this statement, that silicon is having better thermal stability than germanium. It's only because the leakage current of silicon is less as compared to germanium. Leakage current is highly sensitive to temperature. Last is for both germanium and silicon, leakage current doubles for every 10 degree rise in temperature. This statement which I have mentioned in the last point, that the leakage current doubles for every 10 degree Celsius rise in temperature, it's a very important statement. Meaning competitive exam they directly ask that for 10 degree rise in temperature, leakage, what happened to leakage current. So you should be very much clear about this statement. Okay, moving to next slide, your current. We all already have some idea about current. Okay, current is a notation with capital I. It is defined as a rate of change of charge, and in semiconductor the current is bipolar. You know the unipolar and the bipolar, so the current is bipolar, and like in the coming slides I will define you the difference between the unipolar and the bipolar. So for the time being, just understand that current in the semiconductor is bipolar. Now the motive of discussing current over here is that I want to differentiate between the drift current and the current. Current is only the defined as rate of change of charge, but drift current, it is a flow of current in the material or device because of the electric field intensity. You are allowing the current to flow applying some electric field intensity. The current is not flowing on its own. Some electric field intensity is provided, so the current is flowing. So that's why drift means pressure is applied. So with that pressure the current is allowed to flow in the material. Okay, now next is classification of elements. You have three kind of elements: conductor, insulator and semiconductor. First is conductor. All metals are very good conductors of current. Valence electrons are less than or equal to 3. Metals have metallic bonding. Metals are unipolar. Now what does that unipolar means? Unipolar means metals allow single type of charge carrier. Single type of charge carrier flow through the metal, that is electron. They allow only electrons to flow through them. Now we see the diagram of metal figure. I will explain this with figure of these two. and we will discuss it one by one, like what happens at temperature 0 Kelvin and what happens at temperature 300 Kelvin. So temperature 0 Kelvin, what happens is there is no energy gap between the valence band and conduction band. As you can see in the figure that we don't have any energy gap, covalent band and directly your covalent band, and covalent band is filled with electrons. In metals, the density of electrons are very high, that you can say 10 to power 28 some electrons are present in the metal, and in metal free electrons are available even at 0 Kelvin. So that's why you can see at 0 Kelvin you have electrons available in your covalent band, right? In metals, one more statement, in metals free electrons, you can see here, is independent of temperature. And now what happens at 300 Kelvin? When you start increasing your temperature gradually, overlapping take place, and overlapping increase with the increase in temperature. So when you reach to your 300 Kelvin, you can see here that the red is your indicator for the covalent band and the blue is for valence band. And here you have seen that it's a overlapping is occurring here. Now why? Because overlapping is occurred because you have increased the temperature from 0 to 300 Kelvin. So that's why overlapping, you can see here the crisscross represents your overlapping. Okay, so whatever I explained till now, be sure that so that we can differentiate later on insulator and semiconductor. Okay, metals have PTC of resistance. What does PTC means? Metals resistance increase with increase in temperature. Because of the overlapping, as we have seen in our previous figure, overlapping occurred at 300 Kelvin. Because of that overlapping of valence band and conduction band, metal exhibit positive temperature coefficient. That's what PTC defined as. Okay, so metals have PTC of resistance, that means resistance increase with increase in temperature. In metals there is only drift current. Only drift current because in metals there is only electrons, and if there is one charge carrier, that is electron, there is only a drift current. Some good examples of your metals are gold, silver, platinum, aluminium and many others. Gold and silver are, when I tell about you, gold is the best recombination agent and silver is like not too costly. It's also a good recombination agent but generally not used. Platinum, it's costlier than gold, but we don't use platinum in our semiconductor devices. Next is your insulator. Insulator, we all know that's a bad conductor of current. They do not allow the current to flow through them. Valence electrons are like 7 or 8 and they have the ionic bonding among them, and conductivity is 0 because I've already told that they do not allow the current to flow through them. This figure is of insulator. You can see that in insulator the energy gap between the valence band and the conduction band should be minimum of 5 electron volt. It's a need, I mean it's minimum energy gap in insulator. Okay, moving to next slide. Inductors have NTC of resistance. Now I guess you can define what is NTC. PTC was your positive temperature coefficient, so NTC will be your negative temperature coefficient. That means resistance decrease with increase in temperature. Next is energy gap slightly decreases with the temperature. If you remember, I have mentioned this statement with the description in my lesson number 1, so refer that, why energy gap slightly decreases with the temperature. I mean, when you increase the temperature, the gap is going to reduce. Let me show you. This energy gap, like 5 electron volt, it will reduce like little bit, and Then when this energy gap will be like covered up, then conductivity will start occurring. So for the conduction you have to remove this energy gap. So that's why we have the statement that energy gap slightly decreases with the temperature. Okay. Some examples are like air, diamond, ceramic, bakelite, and many others. We have many examples for this. Third is semiconductor. Semiconductor is a device whose conductivity lies between the conductivity of your conductor and insulator. Valence electrons are 4, and one speciality about this is it has covalent bonding, and it is bipolar in nature. Bipolar means the current which flows through the semiconductor is because of electrons and holes both. So when we talk about both electron and hole, it's bipolar. Okay, let's get clear with this figure I have explained here with blue and red color. At temperature 0 Kelvin, what happens? We have energy gap of 5 electron volts, same as insulator. You remember the figure of insulator, same figure. So what I can conclude from here, that at 0 Kelvin charge carriers are 0, and therefore your conductivity is 0. So semiconductor will be working just like as an insulator at 0 Kelvin. So it's a important statement that what kind of device it you can say that at temperature 0 degree Kelvin it behaves like what? Is it a semiconductor, is it a metal or insulator? So at 0 degree Kelvin you should be clear that it behaves like an insulator. Okay, so when you increase the temperature to 300 Kelvin, what happens? At your room temperature 300 Kelvin, because of the thermal energy, a number of covalent bonds will be broken, and equal number of electron and holes were created, and there will be a conductivity in the semiconductor after that. So when covalent bonds will be broken, the holes and electrons will be generated, and they allow the conductivity to flow through. You can see they're almost same electron and holes, not exactly same but almost same, you can say. Okay, again a same statement. The semiconductor have NTC of resistance. Now I think you are very much clear about this NTC negative temperature coefficient. Again, resistance decrease with increase in temperature. Energy gap slightly decreases with the temperature. Same statement. In semiconductor there will be a diffusion current. You remember in metal I have discussed that there is only a drift current. It's only a drift current because there is only one charge carrier present, that is electron. But I'm talking in semiconductor and I'm saying that there will be a diffusion current. Diffusion current is a speciality of semiconductor. Diffusion current means the current is flown because of electron as well as holes. So that's why diffusion current. Example for this is silicon and germanium. Okay. Now the second next is your mass action law. Now what does mass action law say? In a semiconductor can be your intrinsic or extrinsic semiconductor. Under thermal equilibrium, the product of electron and hole is always a constant and is equal to the square of intrinsic concentration. The same definition we have mentioned in the block, and you can see NP represents your product of electrons and holes, and that is equal to your square of intrinsic concentration. Now one thing you have to remember is this law is applicable only at constant temperature. When you have a constant temperature, mass action law is applicable. Okay, the next is this law is widely used for extrinsic semiconductor for calculating minority carrier concentration. When you have to calculate the minority carrier concentration, you can use this law and the formula. like for n-type semiconductor, where you know the n represents your electrons, and for the p-type semiconductor, p represents your holes. So in n-type, the majority carrier will be definitely electrons and the minority will be the holes. So we have indicated with this notation, and holes with p. And for the p-type semiconductor, you know the majority are holes definitely, and the minority will be electrons. So again this law helps you to find the minority carrier concentration. So you can find the minority carrier are holes, and the minority carrier is equal to, how you can calculate minority carrier, I'm talking about that. Okay, so minority carrier will be equal to your intrinsic concentration square divided by your majority concentration. Like majority carriers. I didn't mention the formula because I hope so that what I'm telling you, you can visualize on your own, as I've already mentioned like a lot of description in my slides. So okay, the next is the resistivity. I hope resistivity is very much clear to you. It's the same resistivity we have learned in our physics. We're just trying to relate the resistivity with semiconductor and all in EDC. So resistivity notation is this thing, and your resistivity is a specific resistance of the materials. These two statements, last two statements, you know, I've already discussed. In metals we have PTC, and in semiconductors we have NTC of resistance. And the unit definitely you remember, that's ohm meter or ohm centimeter, any one of these two. Second is conductivity. Conductivity in terms of our EDC, it's just a reciprocal of resistivity. Unit will be 1 divided by ohm, will generate the symbol like this, and unit is like just the reverse of your ohm, so by like meter or by centimeter. Conductivity is equal to carrier concentration into magnitude of Q into mobility. This is the formula of conductivity. I mean, how you can calculate conductivity. There are numericals coming on these formula, so be very clear that whatever formula I'm discussing is very important in like for respective of your exams. So focus on these numericals, and if you get any numerical based on this, you should be able to solve it. So conductivity is denoted by this notation, and that is equal to carrier concentration into magnitude of Q into your mobility. So I can say that your conductivity of any material depends on three things, that is carrier concentration, magnitude of Q, and your mobility. Now conductivity varied due to change in temperature. And like conductivity, why it varied due to change in temperature? It may be due to the variation in your carrier concentration, or maybe the variation in mobility. If there is some variation in these two, there is a variation in conductivity. Okay, in metals conductivity decrease with temperature, and in semiconductor conductivity increase with temperature. In metals, why conductivity decrease with temperature? Okay, in metals, if we increase temperature, your concentration of electron decreases, and when concentration of electron decreases, your conductivity will surely decrease. There's no much of electrons to move through, so how the conductivity will increase? So this is what I conclude, that if you increase the temperature, carrier concentration of electrons decreases, and that allows your conductivity to decrease. And in semiconductor, conductivity increase with temperature. It's so because in semiconductor, as we increase the temperature, mobility of charge carrier decreases, and this will reduce the conductivity by smaller value. And at the same time, because of thermal energy, a number of covalent bonds will be broken, and equal number of electrons and holes are generated, and this will increase the conductivity by a very larger value. So the net result which we get is conductivity increases. So that's why conductivity increase with the temperature. Okay, current density indicated with the notation J. It's a current passing per unit area. In the block we have mentioned the formula, that is equal to I divided by area. I is your current ampere divided by area, that's meter square. Now your J, the density is equal to your conductivity into electric field intensity. We already know the formula of conductivity, just discussed in the previous slide, that it's equal to carrier concentration into Q into U. So in metals we have conductivity is equal to NQ carrier concentration into electric field intensity. I hope this is very much clear to you. You know why I'm writing this is because in metals just we have the electrons. So this thing indicates just the presence of electrons. And NQ, why I'm writing this? N is your conductivity, I have carrier concentration. Okay, so I hope this is clear to you. I'm just putting the values, I'm replacing the values, and you just have to focus on my previous slides to get very much clear about this, because all the things which I'm explaining is in continuation, so every time I cannot show you the previous thing. So I mean, moving to the next thing, you have to be very clear about the previous notations or formulas or everything. So metals have this thing I'm telling about. This is why this in metals we just have electrons, so that's why this thing. In semiconductor we have electron as well as hole, so we have taken the common in the bracket and electric field multiplied with electric field intensity. Okay, so next is important is diffusion and diffusion current. What is that? Diffusion is a natural property, it occurs. Diffusion is defined as the migration of charge carriers moving from higher density to lower density, or you can say movement from higher concentration to lower concentration. Okay, so diffusion is something happening from higher density to lower density, and when something falls from very high distance to a low distance, so that's called diffusion. Falling from up to down, it's natural phenomena. I mean, something falls obviously from up to down, so that's called diffusion. Diffusion occurs due to the change in concentration, obviously from higher to lower concentration. You can see in this figure I have mentioned that diffusion occurs in the semiconductor from higher concentration, indicated with this blue color, and moving towards the low concentration with this red color. So change in concentration is called gradient. Okay, so diffusion is mainly due to the concentration gradient. So remember this thing, change in concentration is called gradient, and the diffusion is mainly due to concentration gradient. Gradient is given, indicated like this, I mentioned in the block. And the diffusion current flows only and only in semiconductor. This is the exclusive statement, you have to remember this statement, that diffusion current flows in only semiconductor and not any other device. Okay, length of diffusion, it depends on four things: diffusion constant of charge carriers, mobility of charge carriers, average lifetime of charge carriers, and your temperature. So from these four things, let's build up our formula. Length of diffusion indicated with capital L is equal to under root D, and I hope D is for what? D is for, I'm talking about diffusion constant, and your tau is talking about your average lifetime. Okay, so under root of both the things. Now you know that diffusion is your mobility into thermal voltage. So length is equal to, you're replacing D with the value this, and you get this final formula. Numericals, focus on the numericals and focus on this formula. Electron diffusion length. So this is a general formula, so let's talk about the electron diffusion length, so and the hole diffusion length. So when talking about electron we just put here in the subscript, and we are talking in the d respect, so I'm just written the same formula with n scripts. Okay, so similarly when we are talking about the whole diffusion length, in the place of n here we have p. Now the thing which you have to remember is your electron diffusion length is never equal to your whole diffusion length. Okay, now electron diffusion current density. Electron diffusion current density is indicated by this formula, and similarly whole diffusion current density is through this formula. And remember that this directly sometimes they ask this formulas for your objective exams, so remember these two formulas. So now you're clear with the diffusion current density and the whole diffusion current density. Now what happens is electron diffusion current. In the previous slide it's like diffusion current density and whole diffusion current density. So from these two formulas we are going to build up our like electron diffusion current, that is equal to your electron diffusion current density into area, and similarly for the whole. And area is always by default consider unit cross sectional area, always by default consider it. Okay, so total diffusion current density in the semiconductor will be the addition of both this thing, because they are occurring because of electron as well as holes. So this thing. Okay, so okay, that's what I have for today, and thanks for watching. I hope you enjoyed watching, and most important is that go through my videos from very beginning, because whatever I'll teach will be related to your previous videos. So if you go through my previous videos you'll find it easy to understand, like go with the flow we say. So guys, do like it and do subscribe yourself, and thanks for watching. Bye bye.